Every year, the world produces over 100 million cubic meters of MDF boards. Picture this. If you laid them out as a road 30 feet wide, you could wrap it around the entire planet at the equator, and that's every single year. But few people know that these perfectly smooth panels aren't born from wood, but from trash, sawdust, scraps, and old newspapers. How does ordinary dust transform into a material that revolutionized the furniture industry? And what secret lies in a process where steam, resin, and hundreds of tons of pressure turn chaos into perfection? Stick around till the end. You'll see what's hidden behind every gleaming piece of furniture in your home. The base for MDF isn't solid logs, but what used to be considered trash: sawdust, wood chips, scraps, and even old waste paper. It's a triumph of resource efficiency. These mountains of wood waste arrive at the factory and first get thoroughly cleaned. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't about cleanliness. The steam is there to soften lignin, nature's glue that holds wood fibers together. Now begins the most critical stage, the one that sets MDF apart from its rougher cousin, particle board. The prepped softened chips get fed into a machine called a defibrator or refiner. Picture two giant metal discs, like millstones, spinning toward each other at incredible speed. Their surfaces are covered with an intricate pattern of sharp ridges and grooves. The wood pulp gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't chips anymore. It's something like fluffy, damp cotton or wood flour. We've just deconstructed wood down to its basic building blocks. Next, this fibrous mass needs to be dried, but it has to happen fast, before the fibers start clumping together, so they get blown into a long, hot drying tube. A stream of hot air catches the fibers, and as they fly through this tube, all excess moisture evaporates out of them. And right here, while the fibers are still hot and swirling in this vortex, the next critical stage happens: resin application. A fine mist of binding agent gets sprayed into the airstream through special nozzles. This is urea formaldehyde resin, our glue. This mist coats every tiny fiber, covering it with a thin, sticky film. It's an incredibly efficient method, guaranteeing perfectly even glue distribution. Interesting fact: urea formaldehyde resin was first synthesized in the 1920s, but it only started being used on a massive scale in wood panel production after World War II. Now this resin-saturated, dry, and fluffy light mass is ready to become a board. It goes into the forming machine. The stream of fibers settles onto a wide moving conveyor belt, forming a thick, loose, and perfectly even mat. Special rollers compress it slightly, and giant knives cut it into pieces of the required length. It already looks like the future board, but for now, it's just a thick, soft mattress of wood fluff. And then comes the climax: hot pressing. This loose mat rolls into a giant press. It might be either a multi-story press that simultaneously compresses an entire stock of boards, or a continuous press that looks like giant caterpillar tracks. And here, two powerful forces act on our mat at once. First, colossal pressure. The press plates squeeze our loose mattress with a force of hundreds of tons, reducing its thickness several times over and forcing out all the air. The wood fibers squeeze together tightly, creating an incredibly dense structure. Second, high temperature, 400 degrees Fahrenheit. This heat does two things. It activates the resin, causing it to polymerize and bond the fibers into a single monolith, and simultaneously evaporates any remaining moisture, which escapes from the board as hissing steam. After just a few minutes in this steel embrace, the loose mat transforms into a solid, dense, perfectly flat, and still very hot MDF board. Pressure in modern presses can reach 700 pounds per square inch. Imagine an adult cow standing on an area the size of a postage stamp. After pressing, the hot boards can't just be stacked. They need to cool down to relieve internal stresses. They're placed in a special fan cooler that looks like a giant card catalog, where they slowly cool down, fanned by air. Once the sheets have cooled, it's time to give them that finished look. First, they're stacked in tall piles and left to rest for a few days. This stabilizes their internal structure. Then each sheet runs through a sanding machine. Picture a giant belt sander with multiple heads. Wide abrasive belts strip away a thin surface layer from both sides, bringing the sheet to a perfectly precise thickness, say 16 or 18 millimeters, and creating that famous paper-smooth surface. And the final touch? Cutting. Massive saws slice the large production sheets into standard commercial formats. After that, every batch goes through strict quality control. Density, strength, thickness, and surface quality all get checked. Modern MDF panels have a density of 37 to 50 pounds per cubic foot. That's 1.5 times denser than natural pine. The finished, perfectly smooth panels get labeled, packed up, and shipped off to furniture factories, where they'll become the foundation for elegant and stylish pieces in our homes, silently demonstrating what a noble journey ordinary wood dust can take. The global MDF market? It's a giant machine churning out more than $25 billion a year. And this machine isn't planning to stop. Forecasts say it'll grow 6% annually. That means demand for this smooth material is absolutely insane. So, who's the head chef in this kitchen? The undisputed king, China. They produce over 50% of all the MDF in the world. Chinese factories run around the clock, churning out millions of cubic meters of boards for domestic use and export. But Europe's no slouch either, with powerhouses like Germany, Poland, and Turkey cranking out millions of cubic meters of high-quality board. German manufacturers are especially famous for innovative technology and strict environmental controls. Now let's talk volume. Every year, the world produces about 100 million cubic meters of MDF. That number is so massive, it's impossible to picture. Let's try anyway. Imagine a road. If you took all that MDF and laid it out as a road 30 feet wide and 10 inches thick, you could wrap a belt around the entire planet at the equator. Generously, an endless stream of material transformed into furniture, doors, and panels for our homes. What's fascinating is that MDF has unique properties you won't find in natural wood. No knots, no cracks, no voids. You can mill it, creating complex decorative elements that would be impossible or way too expensive with solid wood. That's exactly why MDF became the #1 material for kitchen cabinet doors, raised panel doors, and decorative trim. Plus, MDF holds fasteners incredibly well. Screws grip far more securely than in standard particle board. And that smooth surface? Perfect for paint. It goes on evenly, no fuzz, no grain, creating a finish that looks like plastic or even glass. Environmentalists often criticize MDF for using formaldehyde resins, but modern technology allows manufacturers to produce E0 and E-half grade boards, where formaldehyde emissions are lower than in natural wood. And so having journeyed from a pile of sawdust and scraps through a steam bath, defibrator, pressing under hundreds of tons of pressure, and final sanding, this amazing material emerges. Dense, strong, perfectly smooth, and ready to become part of our homes. From humble kitchen cabinets to luxurious carved facades, from simple interior doors to intricate decorative panels, MDF works everywhere, the silent hero of modern interiors. It doesn't demand admiration, doesn't seek glory, but it's what makes our homes cozy and beautiful. And now you know its story, from trash to treasure, from wood dust to a masterpiece of engineering.
Every year, the world produces over 20 million tons of mineral wool, with nearly half of that volume coming from the United States. This is a material capable of withstanding direct flame contact at temperatures of 1,500 degrees Celsius, whilst weighing less than the air trapped inside it. How does solid, heavy volcanic rock, born in the Earth's fire, become a light and fluffy insulator resembling delicate candy floss? How have engineers harnessed fire powerful enough to melt stone to create silence and warmth in our homes? And most importantly, what secret do these enormous factories hide as they transform tons of dirty industrial waste into a clean and safe product for the future? Watch until the end, because what follows is a fact that will forever change your perception of this remarkable stone fleece.
The mineral wool market in the United States is a colossal, invisible machine, churning billions of pounds. We're talking about an industry worth over 4 billion pounds per year. And according to analysts' forecasts, it's only set to grow. This means that right across the country, from the frozen forests of Minnesota to the scorching deserts of Arizona, more and more builders and homeowners are choosing this rock-based jumper for their walls, roofs, and floors. But the story of this material doesn't begin in a factory. It starts deep within the Earth's crust, in the thunderous heart of a quarry. The foundation of it all is basalt. This is a dark, dense volcanic rock, the very material that forms the ocean floor, and which millions of years ago erupted from volcanic vents. But alongside it comes a rather unexpected partner: slag. This is a byproduct from metallurgical giants, a solidified melt of impurities left behind after steel smelting. Once considered worthless waste and simply carted off to landfills, creating entire man-made mountains, today it's invaluable raw material.
Right then, picture the recipe for this industrial marvel. Take several portions of prime crushed basalt for strength, add a touch of slag to achieve the desired chemical properties, and for eco-friendliness and energy savings, generously season it all with recycled glass and offcuts of old mineral wool. All these stony ingredients arrive at the factory in enormous lorries and get tipped into a giant hopper. And now the real inferno begins, quite literally. From the hopper, this mixture, called the charge, flows continuously into an enormous vertical tower, a cupola furnace, or what's known as a cupola. It's a genuine miniature volcano created by human hands. Here, rather like feeding an insatiable maw, they load our stone mixture in layers, along with coke, a special fuel derived from coal that burns with incredibly high and stable heat. Massive fans, roaring like aircraft turbines, pump thousands of cubic meters of air into the furnace, driving the temperature up to absolutely astronomical levels, 1,500 degrees Celsius.
At such temperatures, the stone hasn't got a chance. It melts, cracks, and transforms into a liquid mass glowing an incandescent white. This river of fire flows out of the furnace along a special channel lined with fire brick. The sight is absolutely mesmerizing. A brilliant, blinding stream of molten stone radiating such intense heat that one simply cannot stand nearby without proper protection. And here, at the exit from this inferno, a genuine miracle occurs. The transformation of heavy, viscous liquid into light, airy fluff. This process is called fiber formation. Have you ever watched candy floss being made? A spinning center where sugar is poured in, and fine threads that fly outwards. The principle here is exactly the same, but instead of sugar, molten stone, and instead of a small machine, a gigantic centrifuge. A thin stream of this stone lava hits several massive disks spinning at tremendous speed, making thousands of revolutions per minute.
When a droplet of molten rock strikes such a disk, a colossal centrifugal force instantly stretches it and flings it aside as an incredibly fine fiber, just a few microns thick. That's 10 times thinner than a human hair. Since this process occurs continuously, an entire cloud of red-hot stone threads flies off the disks. It resembles a golden, luminous chaos. Billions of these finest fibers, cooling as they fly, transform into a light, wool-like mass. In just a moment, our heavy molten rock has become airy and fluffy. But for now, it's simply a formless cloud that needs to be gathered together. Whilst the fibers are still airborne inside a special chamber, a fine mist of binding agent is sprayed onto them from hundreds of nozzles. This is a special phenol formaldehyde resin that envelops each tiny fiber.
This cloud of glue-soaked fibers flies onwards and enters the settling chamber. At the bottom of this chamber sits a wide moving conveyor with a perforated belt. From beneath the belt, powerful fans extract air, creating a vacuum. This directed airflow pulls the fibers downward and lays them evenly onto the conveyor, forming a thick, fluffy carpet. This already resembles the future insulation, but it's still soft and the glue hasn't hardened yet. The thickness of this carpet is controlled by the conveyor's speed. The slower it moves, the thicker the layer that settles. And now this golden yellow, fluffy carpet, reminiscent of a giant Swiss roll, is ready for the final stage, baking. It slowly enters an enormous oven known as a curing chamber. This is a long, multi-level tunnel maintained at a temperature of around 200 degrees Celsius. The purpose of this stage isn't merely to dry the carpet, but to bake the adhesive. Under heat, the resin polymerizes. That is, its molecules cross-link into a robust three-dimensional network, transforming into solid plastic that permanently bonds the stone fibers at their intersection points. It's within this oven that mineral wool acquires its final properties. It becomes resilient, capable of recovering its shape after compression. During this process, the resin often changes color, lending the finished product its characteristic yellowish-brown hue. From the other end of this gigantic toaster oven emerges no longer a loose carpet, but rather a solid, springy mat of specified thickness and density. However, it still remains an endless ribbon. Now it's time to transform it into a marketable product. This hot mat passes through an entire system of cutting tools. Sharp circular saws or powerful blades slice it lengthways and crossways with incredible precision into sheets or rolls of standard dimensions, for instance 16 or 24 inches wide, so they fit perfectly between the studs of a timber frame house. The edges are trimmed, and now we have the familiar product before us. And here, another bit of magic happens: packaging. The finished mats or rolls are fed onto the packaging line. A special press compresses them, removing nearly all the air. The product's volume can shrink several times over. Then this compressed block is quickly wrapped in robust polythene film and heat-sealed.
This is done to save an enormous amount of space during transport and storage. It's rather like a vacuum bag for clothes. Instead of a huge, fluffy roll, we end up with a dense, compact package. And when the builder on site cuts through the film, the mineral wool hisses as it draws in air and, like a spring, expands back to its original size within a matter of seconds. The finished packages are stacked onto pallets by robotic arms, wrapped in stretch film, and forklifts carry them off to the warehouse or straight into the back of a lorry. And so, as yet another lorry rolls out through the factory gates, our journey comes to an end. We followed how ordinary solid rock, having passed through the fiery heart of the furnace, became a high-tech cocoon that would preserve warmth, silence, and safety in someone's home for many decades to come. Now for the most fascinating bit, the environmental credentials, because this is where mineral wool absolutely smashes expectations. We've already mentioned it's made from rock and slag. Well, here's the thing. On average, modern mineral wool contains 70% recycled materials. Sometimes that figure reaches as high as 90%. Just imagine, 3/4 of your insulation is essentially industrial waste that's been given a second life. We're talking about millions of tons of metallurgical slag that used to simply end up in landfills, now transformed into a high-tech product. It's one of the finest examples of a circular economy, where one industry's waste becomes another's treasure. Manufacturing giants like Rockwool or Owens Corning process so much slag each year, you could fill thousands of Olympic-sized swimming pools with it.
But that's not all. The second superpower is acoustics. Due to its dense, chaotic fiber structure, mineral wool is an incredible sound insulator. It doesn't just block sound, it absorbs it. When sound waves enter the material's depth, they're forced to navigate through a labyrinth of billions of stone fibers, losing their energy and fading away. That's precisely why it's beloved not only in residential homes for protection from noisy neighbors, but also in professional recording studios, cinemas, and even between floors to avoid hearing footsteps from above. It's like building a personal silent mode into your walls. And finally, the mystery promised at the beginning. Despite mineral wool appearing soft, each of its fibers is a microscopic stone needle. When working with it, these needles can cause mechanical skin irritation, that very itch. And whilst modern technology has made the fibers safer, this stone fluff will always remind you of its true, hard nature, demanding respect and caution.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace. Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock? To do this, it's sent to a heating furnace, where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill.
This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder, and the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod or mandrel is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide. And the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that,
Traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.